kids off is that we use reciprocals and the signs and, all these different words. Take them out if you struggle with it. Use a variable and then see what you would do. Were you guys okay with the first one? And Justin, when you take a square root, when you undo a square, you get a positive and negative. Because don't forget, I could use a positive 2 in here or a negative 2 in here. It's when you see it like this. It's whatever it is in front of it. Is a positive or negative, whatever they designate it as. So we took the square root, and if it's not easy to see this, take its reciprocal. Change this, flip this one, and flip this one. Maybe that's easier to recognize. You see 1 over radical 2? 1 over radical 2, radical 3 over 2, 1/2. Those are you only have 2 special triangles, 3 basic angles, a 45, a 60, and a 90. A 45, a 60, and a 30. The other ones are your quadrant angles. So lay this out, all 4 quadrants. Again, if you're looking for all solutions, you only need to go across the pole on these guys. Find this one, come across the pole, 180 degrees across. If this is 45 and I add 180 degrees, I get 225. That's what this angle is, 225. Just give it to me in radians. So pi over 4 and 3 pi over 4 goes to this one. So add the n pi where n is an integer. Okay? Question? Oh, okay. I called on you too fast, huh?
You always have 180?
When it's across from each other, yes. If I just did the sign and I wanted the positives only, say I just wanted the sign, that's positive. And so then if I give this one radical 2, sorry. If this was pi over 4 and this guy is 3 pi over 4, I'm not going to be able to come across. I can't go this way. So this guy would have to be plus 2n pi. Plus 2n pi. When they're next to each other, I have to do the 2n pi. When they're across from each other, it's like half of a circle around. That's the 180. And just give me the first 2 and do the others plus pi. If you prefer to put this one 2 pi n, I think we talked about that yesterday. If you prefer 2 pi n, it's 2 pi once, 2 pi twice, 2 pi 3 times. Maybe that makes more sense. Setting it up 2 pi n. It's all the same to me. It doesn't matter to me which way you set it up. This one too. Now this one, I don't know if you recognize these. These are also your perfect squares. You could set it up this way. It doesn't matter. It's probably easier to do that. Add 1 and take the square root. Just remember you get the plus or minus. And again, tangent would normally work with the n pi, but we're using all 4 quadrants anyway. So you got both of them, n pi. From 0 to 2 pi, give me all 4, and this is all solutions. Are we okay with the difference between the 0 to 2, 0 to 4 versus all solutions? Like if I ask you for the angles, give me the angles versus give me all solutions, and you have to qualify these. Okay. Yes.
I didn't know there's all solutions.
I should have said it, did I not? It says find all solutions, or you only had to go from 0 to 2 pi. So you only had to give me this. You only had to give me those. But if you're looking for all solutions, infinitely all solutions, then you add the n pi and the 2n pi. Okay. Difficult. I see cosine cubed, I see cosine. Take it out. Go like this. Even this is difficult to look at. You can't divide by x. Remember, when you have a variable, you solve for x. You can't eliminate x. So you have to get this to one side. Whenever you have descending variables, they always come to one side. So bring this over. Now do you see you can factor out? And Can we factor again when we look at this? There's your perfect squares. I can factor completely. Remember, completely? And then I could set each one of these to 0. Once you see it, either take your x and make it back into your cosine because there was only one function, or do it again with cosine in it. Remember, when you divide cosine by cosine, you get 1. It doesn't go away, you get 1. Anything over itself is 1. You could do this one in perfect squares, or you can do this one cosine squared x minus 1. You can add 1 to both sides. You can do this one like that. It'll work out the same. Try not to leave radical 1. Because if you leave radical 1 and you don't call it a 1, you may not see it as a quadrant angle. Remember your quadrants, always use the zeros and the 1s. Now, a little hint. The 1 and the negative 1 only have one angle assigned to it. Where I am at cosine 1, my opposite over here is a negative 1. But any of your zeros always have 2. If my cosine is 0 over here, it is 0 down here. The zeros will have 2. Because then I don't care if the other one's a 1 or a negative 1. I'm only looking at the 0. Okay? So if, like, my thing is saying is if you did your calculator second cosine negative 1, it would pull you out 180. Second cosine 1, it would take 0. Second cosine 0, only going to give you 90. It's not going to give you 270. But it's a good enough clue that if you looked at the 90 and looked at the opposite pole, you'd see the 270 has the same 0. So if you get kind of stuck with your 1s and your zeros, you can put them in your calc. This one was one of the ones we did in class yesterday. Were you guys able to take out the sine squared and put in the cosine, the 1 minus cosine squared in this one? It's just the same as saying if I have 2y squared equals 2 plus x, I can't solve one equation with 2 variables. So the one identity that you have to remember is the Pythagorean identity. The cosine squared plus sine squared equals 1. Now, you can never take out a cosine or a sine. That's the lowest they can be. But a square, I can have this little identity, and I could solve for sine squared by subtracting cosine squared. So if I replace this with this guy, now I have one equation with one variable, and my variable is cosine. One of the biggest things I find is this piece right here. This is on the same side of the equal sign. Don't subtract 2 to the other side. Don't add 2 to the other side. What's 2 minus 2? 0. These 2's are canceling out. They're on the same side. And always make your a, b positive. So divided by a negative 1, it's an equation. Now when you look at them, they both contain a cosine. It's like saying 2x squared plus x. They both contain an x. At any point in your working these problems out, if you get stuck, just put a letter in there. Take the cosine word out of there if it confuses you. See what you should do. So I'm going to take out a cosine. I'm going to be left with 2 cosine plus 1. Set these both equal to 0. So I have an angle whose cosine is 0, and I have an angle whose cosine is negative 1/2. You just unfortunately have to do them both. The cosine is 0. We just set this guy and this guy. And the cosine is negative 1/2. Puts you in quadrants 2 and 3. There's a special triangle. There's a 60-degree angle. So it's 2 pi over 3 and 4 pi over 3. So the solution to that equation is all 4 angles. Now, from yesterday's homework, we learned how to check your solutions. Plug them back in. Put your degree, put your mode in radians, and just plug it in. Pick one of your angles. Sine, say 2 pi over 3, square the sine, equals and hit equals, and then do the other part. And make sure that they're the same values. Leave your calc in radians, it makes it easier. Questions? We're good on that one? Okay.
I still don't know how to get the theta.
How to get the theta? Which part? X? It looks like a trinomial. X squared minus x. Bring everything to one side. You can work the whole thing with x's. And then at the end, replace your x to say secant x. And if you don't like secant, take its reciprocal. Use its cosine. Negative 1 over 1 is still negative 1, so you're okay there. And if you think of your cosine curve, when your cosine curve goes like this, and your secant goes off of it, they hit the same point, don't they? Down up there, or down here, when it's a negative 1. Don't they hit the same? That's the only part they hit, is the 1 and the negative 1. So when I have an angle whose cosine is negative 1, its secant will be negative 1. When I have an angle whose cosine is 1, its secant will be 1.
Where'd you get x equals pi?
X equals pi, because that's 180. So if I look at all my quadrant angles, remember your x value is your cosine value. Even if you put that in your calculator, if there's only one angle that has a negative 1, and that's the 180, the pi. Then I get here, and maybe you want to switch this over to a cosine. As a matter of fact, we did cosine angle up there, and we found that its reference angle was 60. So, but it was in the opposite two quadrants. So now we just have to put them in these two quadrants. Process is the same though. And check these. These are very, very checkable on your calculator. You can even graph. You could put this in your y1, graph it. You could put this in your y2, graph it, and see where they intersect. That's doable. However, it's very hard. You would have to put your calculator back in degrees because it's very hard to recognize a radian when it goes to a decimal. So I'd go back to a degrees if that was the case, or just make the degrees on your table, and you can see it easier. Questions? This one had a little bit of work to it too. This was kind of like the one we did in class yesterday. When we had, and what throws everybody off too is not only do we have two different variables, two different functions, we have two reciprocal functions at the same time. So when you get this down to the end, your goal is each factor that you set to 0 can only contain one function. So we bring it down to the cosecant of x to be 0 and the secant to be 1 over 2. Now, here's your sine curve. Visualize this with me for a second. This is my sine curve, right? Where does my cosecant curve go? How do I draw my cosecant off of this? Say it, go ahead. Yeah, off the little tops and bottoms, off the mids and the maxes, right? Will I ever have an angle whose cosecant is 0? Does it ever touch the axis, x-axis? No, because that's where its asymptotes are, at the 0. So, therefore, this confirms my no solution. What if I wanted to flip this over, take its inverse, I can't divide by 0. That tells me, no, you can't have one. So that part of it has no solution to that part. And I can kind of see that, well, I can definitely see it on my sine curve. Then I come back to here, and this was exactly like the problem before for that part of it. Sometimes I find it easier to view these things if I look at the graph rather than the 4 quadrants. because sometimes it's harder to get that visual picture. Doing your cosecant and your secant off your sine curves really are kind of helpful because they're only like touching at the ones and the negative ones. All right. All right. This one, how many of you had a hard time with this one? Okay. Let's take this one. So again, if I made this a y and this an x, I have two different variables in here, right? I have to replace one. Can I replace the sign? No. That's the lowest that function goes to. Can I replace a cosecant? Yeah, because it's a reciprocal of sine. So I'll replace this guy with 1 over sine. So I bring this down. There's a number of ways you could do this. Now, I have a denominator. Oops, I made a fraction. I have a denominator. So if we multiply all the terms by the denominator, will we eliminate that denominator? So I'll multiply this by a sine of x, this by a sine of x, and this by a sine of x, so that I eliminate my denominator. So this becomes 2 sine times sine is sine squared, plus 1, and anything times 0, 0. So now I have a nice little equation. Subtract 1, and I divide by 2. I take the square root. Uh-oh. Can you take the square root of a negative number? No. No solution. Anybody find another way to do that one instead? You still have to replace the cosecant. But if you take that one, and say you move that guy to the other side, and go back to what? We don't have to use the cosine squared because none of these are squared. But if you did this and you still had to replace this as 1 over sine, the negative, you can cross multiply there as well. And it doesn't matter which one you put the negative on, as long as you don't put it in both places. And you're going to see there, same thing, when you divide, take the square root. You can't take the square root of a negative number. Okay? Make sense? All right. I'm going to bypass that one for a minute. I'm going to bypass this 4 to 6 for a minute. And I'm going to go here. Anybody get this one? Okay. Now, remember yesterday? And I'm going to leave you off at this one. This is your Pythagorean identity. And we said, for you to get tangent and cotangent, you had to divide. So, to get a tangent, I have to divide this guy by cosine squared, right? If it's an equation, I got to divide all of them by cosine squared. The only one you have to remember is this major one. Everything else we can derive ourselves. So cosine over cosine gives me 1. Sine over cosine gives me tangent, and it's a square. And the reciprocal for the cosine is secant. So now, when I come here, I could replace one of these. You kind of have a little choice here. You could take the hard way. You could replace the tangent squared with sine squared over cosine squared. Replace the secant squared with 1 over cosine squared. That would do it. Or you can replace your secant squared, solve here for 1 plus the tangent squared. And do it that way. Far easier. If you replace both of them, bring them down to sines and cosines, like we did in Algebra 2, that would work, but it would take you a little bit longer. So if we replace this with this identity, we're kind of doing the same thing that we did before. Distribute. Now again, be careful. This is on the same side of your equal sign. So you've got 2 tangents squared plus a tangent squared. So I've got 1 tangent squared plus 2 tangent squared. I got 3 tangent squares. I've got a 2 minus a 3. I got a minus 1. And from there you can solve. Good? It's just your other identity you had to worry about.